So curves, here's a curve in three-dimensional space. It looks something like this. Okay, this is a curve. Do you agree? Okay. Now, the best way maybe to imagine a curve is take a hair, right? Especially if you have nice long hair like me. Take a hair. There it is. See, this is a curve, right? A curve. Do you see it? Can you all see? Sorry, I'm holding it. Right? Okay, so that's a curve. Now the question is, how do we study things like this? How does an equation of a curve look like? Okay, and we've seen some curves already. We've seen the most basic curves, which are lines, right? And one standard way of expressing equations of lines was in parametric form. Remember? So a line was given as, so example, a line is, we called it L of alpha, right? But I don't want to use alpha today. I want to use t, because that's more standard. L of t, and then there were three components. One was, it was the point, so x0 plus, we said we'll use capital L because L and M and N were the components of the direction vector. Remember that? So x0 plus LT, y0 plus MT, and then z0 plus NT, right? This was the equation of a line. Does everybody remember this? Okay? And so x was given as some function of the parameter, a linear function because it's a line. Y is given as a linear function of the parameter, t. And z is given as a linear function of the parameter t. In general, a curve is going to be given as points x, y, and z, each of which is given by a function of the parameter t. Okay, so a curve is going to look something like this, where x, y, and z are functions of a parameter t. In some cases, we're also going to have explicit equations which give the curve, just like the more what we call the canonical form of a line. We'll see examples. Okay. So is it clear what I wrote here? Let's do examples. I think an example would help clarify things. So for example, just let me go back one board. T, of course, has to be between some given values. So let's say T is between A and B in general. Okay, so let's do a couple of examples. So for example, look at all the points where x equals cosine of t, y equals sine of t. So maybe let's write it like this. The set, this is the notation for a set, right? The set of all the points x, y, so this is going to be a curve in two-dimensional space, a curve in the plane, a planar curve, such that x equals cosine of t, y equals sine of t, and t ranges between 0 and, let's say, 2 pi. Okay? So x of t is cosine t, y of t is sine t, and we're looking for all the points that satisfy such an equation. Okay? So let's try to figure out what this is. So it's a planar curve. I'm drawing the xy plane. And I'm starting to run the parameter from 0 all the way up to 2 pi and see what points do I get. So for example, when t equals 0, what do I get? What's cosine of 0? 1. What's sine of 0? 0. So I get the point 1, 0. This is what I get when t equals 0. Do you agree? Right? Now I don't want to plug just any general values because I don't know how to take sines and cosines of funny numbers. I know how to do it for multiples of pi or fractions of pi, right? So let's see, for example, when I plug in t equals pi over 2. So this is what I get when t equals 0. I get the point 1, 0. Do you agree? When t, for example, is pi over 2, what do I get? What's cosine of pi over 2? 0. What's sine of pi over 2? 1. So I get the point 0, 1. That's what I get when t equals pi over 2. Do you agree? What happens when t equals pi, for example? What's cosine of pi? Minus 1. What's sine of pi? 0. So I get this point. So this is what I get when t equals pi. I get the point minus 1, 0. Do you agree? And for t equals, for example, 3 pi over 2, you can easily verify that I get the point 0, negative 1. And then you can start plugging points in between, like t equals pi over 4, and so on. And what you're going to get is a circle. So this curve is just a circle in the plane. This didn't come out too round, this circle, but that's the problem with drawing circles. Did my best. I can do a bit better. Okay, and usually we think of t, this is just a matter of how we think of it, we think of t as time. That's why it's called t. So we start at t equals 0 and go all the way up to t equals 2 pi, and sometimes we indicate the direction of t by adding a little arrow here. Okay? So do you see why this thing here is a parametric form of expressing all the points lying on this circle, which I can also express not in parametric form, for example, as x squared plus y squared equals 1. That's the same thing. Do you agree? Does everybody see that? Okay? Good? So let's do some more examples. For example, what about, so let's call this example 1. And this is going to be example 2. What about x of t, y of t equals t squared, where t ranges between 0 and 1. What is this thing? Again, it's a planar curve. There's only x and y. So let's see what it is. When t is 0, what do I get? The origin, right. When t is 1, what do I get? The point 1, 1, which is somewhere here. Does everybody agree? Right? This is x and y. What happens when t ranges anywhere between 0 and 1? The y is always the square of the x. Do you agree? So all the points in between, including the endpoints, of course, lie on the parabola y equals the square of x. So this is going to be this curve. Do you agree? Does everybody see that? Good? Here's example 3. What about the curve? Let's just write this for it. What about the curve? Let's do first, Let's do first sine of t, sine squared of t. What is this going to look like? And let's take t from 0 to pi over 2. When t is 0, I get the point 0, 0. Do you agree? When t is pi over 2, I get the point 1, 1. Do you agree? And for any t in between, again I'm going to get points x, y, such that the y is the square of x. Do you agree? Do you agree that I get precisely this? It's the same curve with a different parameterization. Boy, that's a complicated word. Do you see that? Okay? So I can have two parametrizations for the same curve. Questions? Good? Okay. What about this? What if I take cosine t and cosine squared of t, where t ranges, again, between 0 and pi over 2? Almost. When t equals 0, what do I get? 1, 1. When t equals pi over 2, I get 0, 0. So this is almost the same thing. It's the same curve, but with a different direction. Okay, this is sometimes called the orientation of the curve. Okay, so this is oriented the other way. I start here at t equals 0 and go up to t equals pi over 2 here. Does everybody see that? Do you agree? Okay. We're going to study curves later and see how we find tangents to curves, and the parametrization is not something you can ignore. It plays an important role. But at this point, in fact, these two look very similar. The drawing is the same drawing. Okay, good. Question?
Yeah, I want to ask you, like, we need to have the domain because, like, the curve can't be infinite. Like,
it could. I can say, let's take the curve t squared when t ranges between minus infinity and infinity. I can do that. And then you just get the entire parabola. That's fine.
like it's a function or something.
Depending on what the curve is. But yeah, you can have an infinite curve. Okay? Let's do a few more examples. I'm just going to tell you what they are and give you their names. They have very beautiful names. But I'm not going to explain exactly how I got the drawing. That takes a bit of deciphering again. And I wish I had the time, but we're a bit limited in time. So for example, let's say example 5, t minus sine of t and 1 minus cosine of t, where t ranges, let's say, between 0 and infinity. Okay? So this curve is called a cycloid. A cycloid, that's the name of the curve. And what it looks like, and it's not completely trivial to understand why it looks like that. I'll give you a hint, but you can do some reading on your own if you like. It looks something like this. And so on. Okay? And the reason that it's called a cycloid, and I think that even if you open Wikipedia, you'll see a nice little cartoon showing why this happens. If you take a cycle, like the front half of your bicycle, and have it roll on the x-axis, and you put a little reflecting light on the tire, let's say, on the very edge, and light at it, then the trace of that light is going to be precisely the blue line. I don't know if this is convincing when I just do this, okay, but that's how you kind of, that's the geometry behind the name cycloid for this curve, okay? But try doing this, try studying this. Another famous one that I would like to mention is cosine to the power 3 of t, sine to the power 3 of t, where t ranges, let's say, between 0 and 2 pi. So this is called an asteroid. And what it looks like is something like this. So kind of a star with 4 cusps. And in fact, you can have stars with cusps like this with any number of cusps. And so this is a 4. So this is a specific instance, a 4 cusp, And the general name for things like this, it's called a Hypo Cycloid. Hypo Cycloid. And the specific one is called an asteroid. The way you get these is you take a big circle and have a little circle run inside it. And there are children's games that you can draw with these things. I don't know if you know what I'm talking about. There are these little wheels that roll one inside the other, and you put the pen through little holes and you then roll it and you get all these beautiful drawings. Do you know what I'm talking about? Does anybody know what I'm talking about? Okay, so if you have one at home, bring it and show everybody. It's cool. It's really neat, really neat. And this is the kind of shapes that you get. And by the way, this thing can also be written not in parametric form as x to the 2/3 plus y to the 2/3 equals 1. It's the same thing. Okay. I want to show you an example of a curve in three-dimensional space. So all the examples we had so far were two-dimensional, were planar curves, right? I want to show you an example of a three-dimensional curve, and it's going to be a form of a generalization of this circle that you see here, okay? So what I want to do is take the x, the y that give you a circle, but then add a z component, okay? So I'm going to do it on this, and then so remember what we got here is a circle that started at 1, 0 and then rotated around, right? That was this curve. So what I'm going to do now is take this exact same thing, but add a z component. So there's going to be all the points x, y, z. This time they're in space. Okay, and this is no longer example 1. It's example 7, I think, yeah. And now I'm going to add a component, z, and z is just going to be t. Okay? And let's allow t to run infinitely. So now I'm going to have to draw it in three-dimensional space, a bit more tricky. Here's x, here's y, and here's z. And let's do it. So where do I start? When t equals 0, I start at 1, 0, 0. Do you agree? So what's the point 1, 0, 0? It's 1 on the x, 0 on the y, and 0 on the z, so it's a point here. Do you agree? That's where I start. This is 1, 0, 0. Right? Now, as I rotate, the x and the y, I know how to trace them. They just circle around. And since I'm allowing t to go beyond 2 pi, so every 2 pi they complete a full circle. Do you agree? But as I do that, the z value has to go up, has to ascend. So what I'm going to get is something that looks like this. I'm rotating here with the x and the y, but the z is going up. Do you see that? Right? Can you imagine that? So I'm going to attempt to draw it. So it looks something like this. I'm actually going up the z. It looks like I'm going down because I'm just coming out at us. Okay, but it's something that looks like this. Clear? And in fact, if I want to be really accurate, this is the front and this goes in the back. That's so the professional name for this thing is a helix, often called a slinky, because that's what do you know what a slinky is? Those amazing helixes that know how to jump stairs, right? But can you imagine it? Okay, or like some very nice buildings have staircases that look like this, right? In fact, you have a helix in every cell of your body. In fact, it's a double helix. It's 2 of these wrapped around each other, and that's what DNA looks like. Did you know? You knew that. What? Your genetic code is DNA looks like a two helixes which are kind of intertwining together. Okay? So is it clear what this is and why this is the parametrization? I should just add the orientation. Why this is the parametrization of this shape, of this curve. Clear, everybody? Questions? Okay. So in general, I want to just finish with writing the general notation for a parametric curve. And the reason I didn't start with it is because it looks scary. But in fact, it's just precisely what we've been doing in these examples. So it's not scary. It just looks scary. So in general, parametric curve, or a curve in parametric form, is the set of all points x, y, z, let's do it in 3 dimensions, such that x is some function of t, x of t. I'm abusing notation by calling the function x and the variable x. If you want, you can write x equals f1 of t. Maybe let's do that. I'm not sure. X is f1 of t, y is f2 of t, and z is f3 of t. So each component is given by some function of the parameter, and t itself ranges between some a and b, which are allowed to be infinity or minus infinity. So that's the general form of a parametric curve. If all these functions are continuous, then it's a continuous curve. Okay? So if f1, f2, and f3 are continuous, note that these are good old Calc 1 functions, right? These are functions of one variable. If these are continuous, then the curve is continuous. Which intuitively means that you can draw it without lifting your marker off space. Okay? Okay. Just one final remark. And this may be confusing, but it's important for things we're going to discuss later. So we haven't discussed functions yet. Everything we're doing is building up towards being able to discuss functions. Those are still the main objects of study in calculus. And a curve is a sort of a function, which we haven't encountered yet. So remark, a curve is a function how do I want to call it? Let's call it f from R to R3. R3 is 3-dimensional space. So for any point t, so this function takes a point t and sends the point t to x of t, y of t, z of t. So it's a correspondence that takes points t in R and sends them to points x, y, z in R3. Do you see that this is a function? Clear? So it's a very different function. This is no longer a Calc 1 function, because the domain is still R, but the range is now R3. Okay, so curves are our first encounter with functions whose range is not just R. Clear? Do you see that? Do you understand what I'm saying? Okay, and we're gonna discuss this and what it means and how to work with these functions in a lot of detail, but that's going to be at a later time. Okay, questions about curves? Good? Okay, so let's wrap this one up here.